to have. Then you should make me co-host as well.
Oh, yeah.
Okay, I think we can start. So today it's a great pleasure to have Elchanan Mossel from MIT and Timo Vidgas from Chalmers, and we're going to start with a survey talk about opinion exchange dynamics from Elchanan Mossel. The floor is yours.
Hey, thank you. Thank you, Nina and Julian, for organizing this seminar. Thank you for all of you that are coming. I see a lot of people who I haven't seen in a long time, at least. I see Yuri Kiefer, who taught me probability some millions years ago, and a lot of friends and other colleagues here that I'm happy to see in this forum. So it's good to see that it's a success. And I think one of the nice things, I'm sure Timo would agree with me, I mean, the people who do look at this kind of exchange dynamic or opinion exchange dynamics, and I think the next talk is to some extent in the same broad area, really like this area. And I think there's a lot of interesting questions here in probability theory. And I think what I will try to do in my talk is I'm going to try to give a very, very high level survey of, some of the new motivations for this area and the most classical models in this area. There are many, many models in this area, and I would say maybe most of the models involve probability, but I would just give you the two canonical maybe models in this area, and then I will talk a little bit, depending on time, I will talk a little bit about a less popular area that I and some collaborators worked in. And I understand that that's always the case, but feel free to ask questions in the chat, and if I say something that's obviously wrong, feel free to interrupt me. Okay, so let me this area existed for a long, long time. Some of the models that I'm going to present go back to the 50s or the 70s of the previous century. But I think this area has a lot of new interest in the context of how people form their opinion, in particular in the context of interaction with others or with media. I think a lot of the motivations come these days come from trying to understand the effect of peers. How is it that if you go to a seminar, how does this affect your opinion on various topics? And of course, from the big money perspective or from the political campaign perspective, a lot of the interest is understanding the effect of advertising campaigns, which we won't really get to in any of what I'm talking about right now. I think there's some of the mass and the probability is in the correct model are not there yet. And I think there's a lot of interesting work to be done there. And again, to some extent, I don't know if you would call it a success, but there is an empirical success of controlling or manipulating people's opinions at a huge scale. And I'm sure everybody knows that what Facebook does to many people's opinion, the Cambridge Analytica story, and the political implications that it had both in the US and in Europe. And I think, there's something, I think it's a very interesting body of work to look at. Some of it is not well mathematically founded, or I would say even most of it is not mathematically founded. And what I'm going to talk about today are all the models that are mathematically founded. I don't know if I should write this, given that this is broadcasted online, but I really recommend this book if you want to read about the Cambridge Analytica story. And so you can see all the letters. This is an asterisk. So that's a very good letter. It's almost give you the mass of what they did, right? So it's a popular book, so it doesn't actually tell you the mass of what they did, but it sort of tell you the mass of what they did. So I'm going to try to, in the next maybe 10 minutes or 15 minutes, I'm going to talk a little bit about the theoretical work in this area, and then I'm going to concentrate on the martingale models, which I really like. Okay, so like I said, there are thousands of papers in this area. I'm not going to do justice to any of them. Of course, I'm going to promote one survey. So especially for those, so there are many surveys, in economics and in advertising and in many areas, and I don't even claim to know all of them or even the most relevant ones. But I think one survey that's appropriate for somebody who has a background in probability and want to work in this area, at least to get a feeling for what are some of the models in question, is this paper that we wrote with Omer Tammuz some years ago. It's called Opinion Exchange Dynamics, like the title of these talks. and it appeared in probability surveys about 4 or 5 years ago. And I mean, I think that could be a good entry to this field. Again, it doesn't cover all the models, but maybe it gives you some feeling for some of the models in this area. Okay, so what I'm going to, so this is sort of a very high-level introduction. What am I going to do in the next maybe 10 minutes? I'm going to review the most 2 popular models in 2 areas. I'm going to, first of all, since this is a token probability, I'm going to give a very quick review of the voter model. And then I'm going to review, so this is a very popular model in probability. Then I'm actually going to review a much, much more popular model, which I suspect many of you haven't heard of, at least in the way I'm going to describe it, or the way it's called here. This is called the Groot model, and that's a model where there's, again, thousands of papers, I think, just on these models in economics. And I'm going to review these 2 models. These 2 models have a very intimate connection to probability. And then I'm going to talk about our own work. And I'm going to talk about these martingale models. So these models I like a lot because they sort of have more somehow in the intersection of probability and economics. These models were actually invented in theoretical economics. They were not invented by the probabilists. But maybe the key feature of these models, which of course people in economics knew, is that each person on its own is a probability expert. So each person can compute any conditional probability completely accurately. So that's what they call rational in the economics literature. And that would actually mean, as we will see shortly, that the opinion that these people hold are martingales, right? So there's a lot of martingales that are interacting with each other. So I want to give you a little bit of a flavor of this area. Okay, so maybe just to see how many of you are alive and are not bots, since I'm talking about opinion exchange dynamics, raise your hand if you heard about the Groot model. Oh, can you raise your hand electronically? I think you should have the option to do it electronically. I see 1 hand, but probably I don't know what it means. I see 1 hand up, 2 hands up, 3, 4. Okay, very good, thank you. Now lower your hand, please. Okay, I see, very good. See about maybe 10 models, very good, 10 hands. Now raise your hand if you've seen the voter model before. I expect more hands here. I see many, many hands. Okay, so I think at least half of the people have seen the voter model before, so I will really go very, very quickly over the voter model. And then I will actually also go very quickly about the Groot model, because the Groot model, one of the reasons it's so popular in economics is that, thank you very much for the feedback, everyone. One of the reasons it's so, so you can lower your hands if you want, is so popular in economics is that it's very, very simple. Okay, so I'm going to talk about now for really, this is essentially what I've written about the voter model. So I'm going to talk about the voter model on the graph. And I think Timo might give a better introduction. So let me say what it is. So all of our models are going to be models on graphs. So let me draw the kind of graph that we have in the voter model. It is an undirected graph. So maybe our G looks like this. Maybe, I don't know. I didn't prepare this graph in advance. Maybe our graph looks like this. And then what is the voter model? So you can do it either in continuous time or in discrete time. Let me just do discrete time, so it's simpler, but it doesn't really matter. So I pick an edge uniformly at random. Okay, so I pick one of these edges, this edge. And then there's going to be opinion on each edge, on each vertex. So there's going to be a set of original opinion. Maybe this is a plus, this is a minus, this is a plus, this is a minus, and this is a plus. And then there's going to be a rule of what am I going to do with this edge? What are the transitions? So the transitions are the following. From plus to plus, I always go to plus plus. For minus minus, I always go to minus minus. But if I have, say, plus minus, then interesting things can happen. With probability 1/2, I go to plus plus. And with probability, sorry, this is 1/2, I go to minus minus. And similarly for minus plus. It's the same transition. Okay, so what is the story that we're telling here? I mean, the story that we're telling about the voter model is that, you know, people interact. The interaction is given by an edge. 2 people talk to each other. if they have the same opinion, nothing happened. They stay with the same opinion. If they have different opinions, maybe one of them convinces the other, right? So that's one explanation for the voter model. Of course, you can pick vertices, you can pick edges. There are hundreds and hundreds of variants of this model. I'm not going to talk about them. But why do we like this model? So why is it nice? So it's kind of, the model itself is a good model, right? So it models interaction. Or interactions. The other reason that we like it is that this process is a Markov chain, right? XVT is a Markov chain. And we like Markov chains. And moreover, if you think about it, if you look at the connected graph, which I'm only going to look at the connected graph, the absorbing states, so it goes eventually either to the state all plus or to the state all minus. Eventually, everybody is going to agree that these are the only absorbing states for this Markov chain, so we are going to reach consensus. Okay, so that's very nice, right? We have a Markov chain, people talk, but eventually they all agree, they don't fight anymore, they don't argue anymore. And then the other thing, so we have a Markov chain here, and that's one reason we like it. The other thing the reason that we like it, there are natural martingales here. I think in this model, in the way I presented the model here, it's very easy to see. In this model, in other variants, there are different martingales. So if you look at the sum over all vertices XVT, this is a martingale. Or a random walk or whatever you want, it's a martingale, right? So if you have a plus minus, you're equally likely to go to have one more plus, as equally likely to have one less plus. So, it's going to be a martingale. Okay? Okay, so that's the voter model. A lot of papers about it. That's the models that people like in probability. You can, given that it's a Markov chain and a martingale, you can ask what's the probability that I'm going to end up in all plus and all minus. This is just a question about random walk, and there are a lot of variants of this model that you can study. Okay, good. So many of you have seen this. This was just a recollection. Okay, so that's what I said. It's a Markov chain. And it's a martingale, and this is why we like it. We can analyze it. We can say a lot of things. Now I'm going to tell you about the deGroote model. And the deGroote model is in fact not a random model. There's no randomness. So I said there's some connection in probability, but there's no randomness. Okay, again, we are on a graph V. And now the opinion are going to be, they are not random variables. I'm going to denote them by small letters. And let me just make the opinion maybe XVT is going to be in the interval, say, -1, 1 for all V. Okay, so maybe this is where you are on the political spectrum between the left and the right. So this is some number between -1, 1. -1 means that you're die-hard left-leaning person. 1 means that you are very much to the right. But then you talk to your people, to your friend, and how do you do it? Well, what encodes the information here is a V by V. Okay, V again is the number of vertices in the graph, or the set of vertices in the graph. Stochastic matrix. This means the sum of the rows of each row is 1. And then the interaction is that xt plus 1 is equal to m times x of t. Okay, so let's see what it means, right? So let me draw a little graph here. Maybe, I don't know, what's the smallest graph that I can draw that would make sense. So maybe this guy gives 0.1 weight to this guy, 0.2 weight to this guy, and 0.7 weight to itself. And then similarly, maybe this is too small, this is 0.5 and 0.5. So that's the model. And maybe this is because I have no space, this doesn't listen to anybody, and it goes to itself as probability 1. It just listens to itself, right? So that's the model. And then there's going to be some initial opinions. So maybe so maybe the initial opinion, x at time 0, is going to be, okay, so this is too small maybe, but this vertex is going to be, let me point. This vertex is going to be maybe vertex number 1, this is going to be vertex number 2, and this is going to be vertex number 3. And maybe the original opinions are, I don't know, I didn't think about it in advance, but 1, -1, -1, right? So people start very extreme, okay? 1 is on the right and the two other are on the left. And then what will happen at x1 Well, you're going to take some averages, right? So what is the first coordinate going to do? So say, well, I'm going to take 0 times 7. I'm going to take 0 times 7 times myself, plus 0 times 1 times this number, plus 0 times 10 to this number. So it's 0.7 minus 0.3, so it's going to be 0.4. And what is this guy is going to say? I'm going to do 0, half, 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 half between -1 and -1 is still -1. And this guy is just listening to himself, so it's also going to do -1. Okay, so I didn't prepare this example in advance. What will this example converge to? Can anybody tell me what will x infinity be in this case? Anybody wants to write in the chat? Okay, so this will converge to eventually -1, -1, -1, right? Because there's this one guy over here that goes to itself as probability 1, and he will always stay -1, and he's not going to change. And for the other things, there's averaging happening, right? There's sort of harmonic stuff happening, so everybody else is going to converge to -1. So eventually, we are all going to converge to -1 in this example. Okay, so this is a completely deterministic model. Why do we like it as people doing probability? So I'll just say why we like it. So people in econ like it, so features maybe. It's very simple. So that's why people in economics like it. Why do we like it? We like it because we know a lot about Markov chains. Markov chains. And we have a Markov matrix here, right? We just apply the same Markov matrix over and over again. There's no sampling happening, right? It's a deterministic vector, and I'm applying the same Markov matrix over and over again. But we know a lot about Markov chains, right? So I'm just going to give one example, e.g., if the chain is ergodic, right? So there's a Markov chain that corresponds to this matrix, and all converge to the same opinion, all agents converge to the same value, And we can even say what this value is the sum over all vertices in V, pi of V, where pi is the stationary distribution of the chain, times x v at time 0. Okay, so this is what we know from the theory of Markov chain. So in fact, a lot of literature in economics either uses the literature that we know on Markov chains or sort of reinvent stuff that we know in this dual language to prove many, many results about this deGroote model, which we know is just, a lot of it is just analysis of Markov chain. And maybe I'll just give you one name in economics if you want to start looking at the various versions that people look at. So there's Matt Jackson at Stanford is one of the leading economists who is using this model and studying this model. Okay, good. Questions about, so I just wanted to give you a flavor of two of the simplest model. It's by no means a survey of all the models that we know, but I just wanted to give you a flavor to tell you where a lot of literature, both in probability and in economics, go. And then I'm actually going to switch gears and go to talk a little bit about this model that I like the best, which is a little bit more sophisticated.
Hanan,
yeah.
Do they use products of random stochastic matrices?
So I haven't seen that. That's a good question. I haven't seen that. For them, the model is really what this matrix models. It's modeled your interaction between people, right? So maybe you talk to your wife. Whenever you listen, you see what your wife says.
But maybe every day there's changes.
I haven't seen literature like that. It could be interesting to apply this theory. As far as I know, I haven't seen it, right? So it could be interesting to find a situation where there's a good distribution over matrices that are changing and then applying a product of random matrices. It's the first time I hear this idea, right? So it could be interesting to apply this. Thank you, Yuri. Yeah. Great question. Okay. So I don't know what are Jackson networks. Somebody is asking me. This is Matt Jackson is an economist from Stanford. I'm sorry, I don't know what's Jackson networks. So I can look it afterwards. Okay. So that's what I said. We can apply what we see for Markov chain. Okay. So now I'm going. So this was sort of the warm up. I hope it's a good introduction both for what I'm going to do in the next half an hour or so, where I'm going to tell you a survey also. It's very high level. Some of the newer results in this maybe slightly more sophisticated models. And I want to go over this more sophisticated model right now. I like it. I think it's an interesting model for probability audience. Even, us giving exercise in the grad probability classes, I gave exercises from this field. We don't really often think about interacting martingales that interact in exactly this way that I'm going to talk about. Okay, so here's the model. Let me tell you what it is. I'm going to talk about these martingale models on directed graphs. So as before, we will have a graph. This time I'll have it directed, right? So directed just means that, I have maybe 3 nodes, and this points to this one, this points to this one, this points back and forth, and this points to this one, right? So points would mean in the things in terms of modeling social phenomena, points would mean observes. So I have these 3 nodes here. Let's give them names now: 1, 2, and 3. Node number 1 observe only nodes number 2. Observe node number 2 and node number 3. Node number 2 observe node number 3. And node number 3 observe node number 1. Right? So we really think about it as people observing other people. Okay. Okay, so let me go over all of the parameters. Sorry, the graph disappeared already, but let me go over all the parameters of this graph. So we have this directed graph. Now there's going to be something that we all want to know. The thing that we all want to know for simplicity is going to be a plus or minus 1. It's going to be the state of the world. So, maybe you're economist, +1 means the market will continue going up next year. -1 means it will crash next year, okay? And this is a priori a Bernoulli random variable. And now come maybe the most interesting aspects. We get information about the state of the world. So every agent, okay, this is where the IID or the IID structure of the probability comes in. Every agent or every node in the graph gets a sample from Fs. What is Fs? So let me write what Fs is. So Fs is equal to some distribution F plus if S is equal to plus, and some other distribution F minus if S is equal to minus. This is just a compact way of writing it down. Right? So, if the state of the world is plus, you're going to sample IID from some distribution. If the state of the world is minus, you are going to sample from another distribution. There are some conditions that you need about this distribution, which don't actually matter so much, or they matter a little bit. So, but let's just for concreteness, just imagine that F plus is this guy, and F minus is this guy. Okay, that's the density of F plus and an F minus. Okay, so it's 2 different distributions, right? So this is dF minus and dF plus. Okay. Okay, so we are all living in a graph. We want to know what is S. Every one of us gets some information about S. The information that we get is indirect in the following way. If the state of the world is plus, we get it from F plus. If the state of the world is minus, we get it from F minus. Okay, now I'm going to start talking about the opinion exchange dynamic, right? So, and I'm going to do it in the language of probability. We are each going to have information. We are going to have a sigma algebra. So agent V information at time 0, or the sigma algebra of information that they have. The information that they have is just the signal that they got. They got some information. That's the information that they have. Okay, so that's not so exciting. Now, given this information, they are going to try to estimate what's the state of the world. So we are going to have this random variable xv. So xv at time 0, that's the posterior for S. So I want a number between -1 and 1. So it's just the conditional expectation of S given the signal that I got. So I got a signal. Given the signal, I have some probability that S is +1 or -1. It's more compact for me to write it as the expected value. It's some number between -1 and 1. And here comes the twist, or the new aspect. I'm also going to take an action. Okay, so AV is 0, and there are going to be more A's. This is my action. And this, in the world of economics, this is my belief. Okay, my belief says, what do I think if S is +1 or -1? Action is what other people are going to see. So there are much, much more general models, but I choose just this simple model where you see a lot of the phenomena. If the posterior is more likely to be plus, I'm going to say plus to all of my neighbors that can see me. If the posterior is more likely to be minus, I'm going to say minus to all the neighbors that they see me. Okay, so I get my signal, I estimate the posterior probability, and then if it's more likely to be plus, I say plus. If it's more likely to be minus, I say minus. I did not reveal my posterior in this model. Okay, just what's more likely. So that's step number 1. Let's see what happens in the following up steps. So this is step number 2 and 3 and so on and so forth. 2 and 3 and okay, that's what's going to happen in the rest of the step. So how is my information going to change? So at step number T, well, I'm going to look at, I write it in the terms of linear of sigma algebras, but I'm just going to say it in word. I have all the information that I had before, that's sigma vt minus 1, and I have some new information. What's the new information that I have? It's all the actions of the neighbors that I observe. Okay, so what's new? I only get at the beginning a signal about the state of the world. From that point on, I only see what my neighbors do. My neighbors do plus and minus. I said, oh, Nina did plus. Okay, so Nina did plus, so probably it means that, So at the first step, it's pretty easy, right? If Nina did plus, I can say what, there's something that happened with some signal. But in the next step, it's becoming more complicated because maybe in the next step, Nina said minus. Did she say minus because I said minus, or because Julian said minus, or because Yuri said minus? Some of these people I see, some of these people I don't see. That's a complicated computation that I can do, that I can or cannot do. But what's nice about this martingale model is I can compute any conditional expectation that I want. So I will just compute the conditional expectation, given that, say that I've seen that Julian said at the second step minus and Nina said minus 2. Okay, so let's see what it, right? So once I updated my information in the way that I said before, so this is the new information, then at time t, I'm going to have a new posterior. So it's the expected value of S, what I want to estimate it, given all the information that I've seen. Again, the information that I've seen is the signal that I've seen at the beginning, plus the action of everybody that I observe. And the action is going to be, again, if it's more likely to be plus, it's going to be, I said plus. If it's more likely to be minus, it's going to be minus. Okay, so maybe let's just give us a very simple example with Nina and me. Okay, so we both try to estimate the chance that this YouTube of this talk will have more than 1 million views. Okay, it's probably not going to have more than 1 million views. Let's say more than 100 views. Okay, so we want to estimate the probability that it's going to be more than. So I get some signal, maybe because I estimate, I know how my talks are going in general, and Nina has some signal, and then we are going to have this discussion where in parallel I'm going to say more, and she's going to say yes, and then I'm going to say more, and then she's going to say yes, and then she's going to say more, and then I'm going to say yes, and we're going to continue discussing like that forever in principle. Is the model clear? Okay, and right, so in general, it's not just two people, right? We'll have again this social network, we'll have this graph network, right? Maybe, these people all observe each other, and maybe at the first round, this is a plus, this is a minus, and this is a plus, and then everybody update their opinion. So this would be at step t equal 1, and then step t equal 2, maybe people will update to plus, minus, minus, and then and so on and so forth. Right? They will update according to these rules that we said here. Okay, so why do we like this model so much as probabilists? We like them for the following fact. Again, this is something that economists knew for very, very long, is for each v, if we look at the process xvt as it changes in time, this is a martingale. Why is it a martingale? We are just looking at the conditional expectation of some random variable, given finer and finer sigma algebras, given more and more information. Right? So if we look at the expectation of a random variable given more and more information, we know that this is a martingale. So that makes us happy, right? And moreover, this is a bounded martingale, right? It's a martingale that's bounded between -1 and 1, so there's a limit, right? So we don't have to do anything fancy. Everybody's opinion, belief is going to converge. And we are going to write x of v for xv at time infinity, which we can call the limiting belief. Okay, so why is this model again interesting for us from a mathematical perspective? We have different xv's. Each of them is a martingale. Martingales we like. This is a simple martingale. It converges easily because it's bounded to a number between -1. But these martingales interact, right? So these martingales interact, and then we want to understand what's the effect of the interaction between these martingales. Yes, so it's sigma is sigma algebra, right? Is the sigma algebra? Somebody asked, right? Thanks. Sorry if I missed some other questions. Okay, so let's see what other question we can ask about this, right? So each of us individually is a martingale. I want to tell you about maybe 2 of the main theorems, and maybe on one of them I'll tell you a little bit about why the proof is interesting. And then I want, if I have time, I'll talk about a large deviation version of this model. So there is a long line of work that leads to this theorem, and I won't try to say exactly who did what. So it started by work by Uman, who won the Nobel Prize in Economics, Memorial Prize in Economics, partially for this work, not exactly for this model. And then more relevant for this model is this work of Rosenberg, Solan, and Viel, and Gale and Kariv. And this statement, which is slightly stronger, is in this work with Alan Sly and Omer Tammuz. So under some conditions, these are conditions 1 and 2, which I'm going to explain in a second, everybody is going to eventually take the same action. So then either, and there's a caveat, either the limiting belief of everybody on the network. So remember, XV is the limiting value of the martingale at the vertex V. So this is going to be a number between -1 and 1. So all of them, all of the vertices are going to take the same action. They're going to say it's more likely to be plus, or everybody's going to say it's all likely to be minus, with the caveat that it could be that everybody will be indifferent. Everybody will say it's equally likely to be plus and minus, right? So this never happens, but we don't quite know how to prove that it never happens. But eventually everybody agrees, either in the sense that all of them know nothing, or in the sense that all of them say that plus is more likely than minus. They do not agree, so the comment here, it's not true that XV is equal to XW for all V and W. Okay, this is the actual belief, right? Even if Nina and I discuss if there's going to be more than 100 views or not, and Nina got a signal that it happens with probability 0.9, and I got a signal with probability 0.8, so what will happen in our model? Nina will say yes, I will say yes, we will just reaffirm another opinion. I will update my probability a little bit, maybe from 0.8 it would be 0.83, and maybe Nina will update her opinion a little bit, from 0.9 it will be 0.92, but that's it. Then nothing else is going to happen. So our actual posterior these probabilities are not the same. It's just what we think is more likely is going to be the same. Okay, so that's what happened in this model. So let me say a little bit about the assumptions here. So one assumption that's very strong, so maybe I'll talk first of all about this assumption number 2. What is an, oops, again I'm doing this. What is the assumption? It's strongly connected. So here's an example where that's not the case. Again, I'm drawing like this. So maybe this is Nina, and this is me, and this is our graph. Nina observes me, but I don't observe Nina. So there's no reason that we will agree, right? Nina has some information that I do not, so we will not agree. So this graph is not strongly connected. Strongly connected means there's a directed graph from every point to every other point. Directed path between any 2 points. And the other assumption is about tie breaking. And the formal way to state it is to state, and we will assume this from now on, is that df plus to df minus, is non-atomic. So what does that mean? Right? It could be, for example, that the signal that Nina and I get is completely unrelated to the question. And then df plus to df minus will be the constant 1. So this is not a very interesting case, right? If both of us get exactly the same distribution, if it's plus or minus, then df plus to df minus is going to be the constant 1. It's going to, the relative density between them is going to be 1. And then nothing interesting is happened. There are other cases where df plus to df minus is atomic. And basically, you can't really say what happens in these cases because you have to deal with tie breaking. What do I do if I think it's exactly equally likely to be this or that? But I said I take the sign. Then you have to say, what is the sign of 0? And then you say, oh, let me decide that the sign of 0 is always plus, but then the model is not consistent anymore, so you get into trouble, right? So somehow, in order for this to make sense, you want df plus to df minus to be non-atomic. Okay, and if it is non-atomic, then everything works out. Oh, very good. So somebody already asked me the next question. Very good, Julian, you predicted well. So excellent, everybody is converging to the same thing, but do they converge to the right thing? But is it true that S is equal to S prime? Almost surely, right? What do you want? So what do we want? We like the fact that they're martingales. They are rational people, their opinion converge. We like the fact that they all agree. but we would like them to agree on this, on the correct thing, not just to agree. Okay, so that's a natural question. So the first answer is just trivially no. Okay, so what would it be? Let's look like at, so answer one is no. And the example is going to be one agent. Okay, so, you know, and remember, we have the same signals that we had before. This is F plus. This is the density of F plus, and this is the definite density of F minus. So, you know, suppose the true state of the world is plus, but, you know, Nina was unlucky. So for, you know, you being unlucky, maybe I'm unlucky, and she got this signal here. If she got that, this can happen with, you know, constant probability that she gets this signal here. And then in the signal you ask, is it more likely to be plus or minus? So it's more likely to be minus. Nina is going to say minus. Now nobody is going to change her opinion, and she's going to be wrong. So obviously with one agent, the answer is no. But I think what Julian meant to ask, so a final question, but how about many, or maybe infinitely many agents? Right, so you don't really expect that one agent will be correct. They get noisy information. If you get a lot of information, you know, you'd expect something like the law of large number to hold. So, you know, you get a lot of IID copies of something that's correlated with S. You know, you should be able to recover S. And that's, again, indeed the question that we're going to study next. So I'm going to give you an example, which, I mean, we used it in this setup. Economists use related example for other models. So here's an example of the royal family. This is an example of which I like to call the media. So once there was the royal family that everybody listened to, now let me call it the media. So here's the media. So we all live in an ideal society in terms of Facebook and all the networks and so on and so forth. We have very, very few friends. So we live in an infinite, undirected line. So if each of us has only two friends, then we talk to them bidirectionally, right? So this is it. And, you know, and here's the media. The media is maybe a clique of size 5. Okay, so this is K5. Everybody is connected to everybody. And everybody listens to the media. So this is the directed edge from everybody to the media. The media doesn't listen to everybody, but everybody listens to the media, right? So that's how the media companies would want to control us, right? There's 5 companies, we all listen to them. We have very, very, very weak interactions between each other. And we want this graph to be strongly connected. So maybe the media also listens to this one person. Okay, so they listen to one person, maybe the person number 0 they listen to, but they don't really care about anybody else. Okay? So obviously this graph is strongly connected, right? You can get from any point to any point, right? You know, there's a directed path from any point to any point. But what's happening in the media in this example, with constant probability, S prime is equal to minus S. So let me explain what's the mechanism that leads to that. Well, with constant probability, so I'll explain why. So this is a bad example, right? This is an example sort of in the opposite direction of the law of large number, right? There are infinitely many people who at the beginning get an independent copy of the signal. In principle, they have tons of information, but in fact, what will happen, they'll all converge to something that with constant probability is wrong, okay? And this is how this happens. This happens because with constant probability, the media is just 5. It's just Google News, Facebook, it's just these 5 companies. With constant probability, they get a signal that's pointing to the wrong direction. Okay? Now, everybody is watching these 5 news outlets. They're also looking at their phones, but the news outlets are much stronger. So already at step number 2, everybody will have the wrong opinion. And from that point on, everybody is going to stay in the wrong opinion. Okay, so this is an example, sort of the law of large number doesn't work. Okay, so I wanted to tell you a little bit about the proof of the following theorem, but one of the results that we really like, and I'm just going to tell you about the statement, is again in the same line of work with Alan Sly and Omer Tamuz. So under the same assumption that df plus to df minus is non-atomic, and the graph G is infinite. So we have two definitions. One is L-connected, which I'm going to explain in a second. The second one is undirected. Undirected means that if I follow the media also follows me. Then in that case, what everybody converges to is the right opinion. Then S prime is equal to S almost surely. Okay, so let me explain what undirected and L-connected. So I'll just say what it is. Undirected means that if U is connected to V, if U is observing V, then V is also observing U. Okay, and L-connected is a relaxation of it. So if U is connected to V, then there is a path of length L. So V going to V1, V2, up to VR, going to U, where R is less or equal than L. So if I observe the media, it's not that the media directly follows me, but it directly follows somebody who follows somebody who follows somebody that follows me. And this is of length at most some constant L, maybe L is 10. Okay? So this result is saying somehow, I mean, philosophically, it says that the law of large number holds as long as there is not too much imbalance between who is following whom. Right? So I want to be the case, right? If it's undirected, if you follow me and I follow you, then it's completely equal in some sense. So if you follow me, I follow you. You can relax it a little bit. If I follow you, then it has to be the case that you follow somebody who follows somebody who follows somebody who eventually follows me. Right. So James asked a good question. I mean, I'm okay. So James is asking a good question as usual. Right. So let me make maybe a quick comment. So comment. So here we're talking about bounded signals. When there are bounded signals mean unbounded signals mean that if I got a signal, I know for sure that something is a plus. If I know for sure something is a plus, then the game is a little different, right? Because I'm never going to change my opinion. And as long as there's at least one agent who knows that for sure there's a plus, everybody is going to agree and we'll have a plus. So this example of the royal family is not going to work. Right. Thank you, James, for asking.
It wasn't so much that I might be sure, but if I have a sufficiently strong signal, I'm still not sure, but I'm sure enough to ignore the 7 other opinions I listen to.
So this example with the royal family is just for bounded signal. Many of the results in this area actually not what I'm talking about right now, actually crucially rely on the question if the signals are bounded or not. Right? So it's not something that I talk about here now, but if you want to look, I mean, a lot of the herding literature. So if you look for herding in economics, these are related models, but not exactly these models, actually crucially rely on the question if the signals are bounded or not, and you really get different results depending on that.
So like the example you had at the beginning is not bounded in that sense, right? Is that right? You had two triangular distributions. If I see 0.1.
The example I had at the beginning was not a good example in that. I have to truncate it a little bit. Thank you, James. Thanks. Good. Okay, so maybe in the last 5 minutes, I wanted to tell you something about the proof. I mean, so the proof is cool, but I'm just saying a cool proof. It uses graph limits, but somehow, I mean, I'll say it in very vague words. I mean, it uses graph limits. Somehow you have to generate. You want to get a law of large numbers, right? So in order to get law of large number, you want independence. And somehow the way to get independence, we don't have a very direct way to get independence. The way to get independence is somehow uses graph limits, right? So it's somehow a very indirect way to get enough independence to derive a law of large numbers in this setting. Right? So this is very, very vague. I mean, even in one hour lecture, it's not clear that this proof is completely transparent. But I think it might be interesting for you if you're interested in law of large numbers in somehow very dependent setups and connections to graph limits. So I want to maybe the last 5 minutes, that's the last slide. I mean, it has multiple, let me just scroll all the way down and tell you maybe just a little bit about large deviation aspect. I know that, many of the people I know in the audience are interested in large deviation. And maybe one last surprising result of this flavor. So this is going to be my last slide. And it's going to be a very similar model some things are going to be simpler, and there's going to be one caveat which is going to be different, not more complicated. So the graph is not directed anymore. Now it's everybody observes anybody. And in fact, it's going to be the complete graph with n agents. Everybody observes everybody. Okay, but you just observe their actions. The reason that we're talking about large deviation now, or the large deviation setup, is that everybody doesn't get just one signal, you get many signals. You get signal at time 0, signal at time 1, signal at time 3, signal at time 4, signal at time 5, and so on and so forth. So then, of course, if you get many signals, and Nina and I are talking, Nina doesn't need me, and I don't need Nina. Right? We get many independent signals, we apply the law of large number, or large deviation, or Chernoff, or something, we know that we're going to be right? So now it's more a question about the rates. Okay, so I'm going to talk a little bit about in a second. The model is the same model, right? The sigma algebra at the beginning is just my signal. Then I take my posterior, is the expected value of the signal given my sigma algebra. My action is going to be the sign of the signal. How am I going to update? I'm going to update by including my original sigma algebra, looking at all the actions of everybody else. Right now it's the complete graph, so everybody is my neighbor. And also I get a new signal, right? So I'm updating according to all the information that I see. I got a new signal, I see everybody else, I do it over and over again. Okay, so again, of course, everything that we said before, it's still true. Everybody is going to agree. It's a martingale. We even know that there's going to be exponential, quickly convergence to the truth for each person because of large deviation. Okay, so the question here is a really different question. It's a question of large deviation. It's a question about rate. And the interesting question that I think we analyzed is, and I'm just going to give you a hint of the result, and a hint of the kind of questions that are asked in this area. So we know that the probability that Nina is going to be wrong decays exponentially with t. Oh, I forgot a log here. So how is the 1 over t times the log of the probability that my action is not equal to s depends on n? How does it depend on the number of agents? So if Nina is on 1, there's a positive, we have a rate, a large deviation rate that depends on the distribution in some number. Now, what advantage does Nina have from observing me or observing everybody else? Do we get a better rate or not? And by how much is it better? Now, the interesting result here is that, okay, I did it in the right. So I did it in the right direction. Again, I forgot the log. So the interesting direction is the large deviation rate, to the best of our knowledge. The large deviation rate does not increase with or does not improve with n. So there is a constant that just depends on the distribution of f plus and f minus, such the probability that Nina is wrong, the asymptotic probability that Nina is wrong, 1 over t times this log of this probability as t goes to infinity, is lower bounded by this constant, no matter how many other agents she observes. I let you digest it. No matter if there's 100 people that Nina observes, or 1 million people that Nina observes, or 1 billion people, a large deviation rate is going to be lower bounded by a number that does not depend on the number of agents. And just for contrast, if Nina observed everybody, yeah, maybe I'm writing it in the wrong way. It's a negative number. Sorry, there's something about the statement that doesn't make sense, sorry. So this is log of it's a negative number. So I think the
minus log instead of log or something. Then
right, so I see them staring look. So I think I'll just change the CF greater than 0, right? So there's just some number, right? So that the probability that you're wrong is bigger than that number, right? So let me just contrast it with what would happen if Nina would observe all the original signal. If Nina would observe all of the original signal, this limit would be some negative number. And if you have n agents, it would be multiplied by n. Because she will observe n times the number of signals that she originally observed, right? So again, I'll just put the context here. If observe all signals, so this means not my signals, but all the signals that we get to everybody, then so I wrote the large deviation very uncarefully. Then the limit is 1 over t log probability AVT is not equal to S is going to be equal to n times some negative constant, right? Because if I observe n times many signals, my large deviation rate is going to be go by a factor of n. C is some number less than 0. Okay, but what's interesting about this result is if instead of observing minus log or making it a negative number, sorry, and thank you everybody for commenting about this typo. But what's interesting about this result that if instead of observing their signals, I observe their actions, then having many more people doesn't help, right? So to some extent, the story that you can tell here is like a story, does it help to have, okay, I don't know want to cut the branch that you're sitting on a tree, but does it help to really have many people doing the same thing and interacting, like having seminars in probability, right? So the naive large deviation result will tell you, yes, the more people you have, the better it is. But this result is sometimes telling you that, unless you actually share all the information that you have, if you share some filtered information, it might actually not help, right? So this result with Matan Ariel and Phil Stark and Omer Tammuz says that, if in the interaction between academics you don't reveal anything, there actually might be something that we call in this paper groupthink. Sometimes in the first step, we all got to the wrong opinion randomly, and then it's very hard to move from there, right? Because then the consensus is that, this is the truth. And even if your signals keep telling you that the truth is in the opposite direction, there's this huge majority of scientists who say the opposite and keep saying the opposite to what the signals that you get over and over again, that you actually do not change your opinion, right? So that's somehow the moral of the story, which I think is an interesting story. Okay, so I'll stop here. Let me just mention that actually we don't know if for this probability there is a rate. This is just a lower bound. So one of the many questions that are open in this area is if there is a rate for this probability, and we don't know that. Okay, so I hope I gave you some interesting examples of this area. I encourage you to look at this literature and think about models. I think for people doing probability, this is really a rich source of interesting problems to look at, and I'm happy to take questions now. Or have a discussion.
So I think James has a question.
Sorry, me again. Lovely talk, Elchanan. Thank you very much. I've got two questions, actually. One was just about that bit at the end. I don't understand why that rate isn't just 0. For fixed n, can't they just converge to the wrong answer? And then
no, so again, maybe I'll repeat the setup. So okay, so let me repeat some basic facts. Okay, you get a new signal at each round.
Oh, I'm sorry. Okay.
So you get so even if you ignore everybody else, you have a negative, positive or negative rate. You have a non-zero rate, right? And it is always true that in this kind of argument, you can also say, I can always ignore everybody else. So my rate is going to be at least as good as that.
Sorry, I missed the bit about getting a new signal each round.
Yeah.
The other question was, so it sounds like these computations might be quite difficult. Do they get sort of exponentially difficult after to decide your action for round T? Sounds like you might need sort of exponentially much computation in T.
Right. So one of the reasons this proof are a little difficult is that it's computing these probabilities, like the probability that are written over here, is extremely difficult. And also, I think what you're referring to is the probability of a specific agent taking a specific action is becoming very difficult. And in fact, in some of our other work that's more computer science, we show that, for this kind of processes that we're talking about now, this, computations are p-space hard, much harder than NP hard, right? So that's, so yeah, and one of the reasons that I think this model didn't have the success of, say, the Groot model is that, the computations are very hard, so it's hard for us, for mathematicians, to do analysis. But it's also a little hard to justify that people actually behave in this way because they have to carry out this very complicated computation. Yeah, excellent question. Yeah. I see a hand by Ganesh.
Hi, Elchanan. Thanks for a very interesting talk. So I wanted to ask, so if you can only observe the action, that's like signaling one bit.
Yep.
If you could signal a finite number of bits of the signal that you observed, would that still not depend on n?
I believe so. I mean, I think the same philosophy of the proof would work. Yeah, it still would not. I mean, there will be a bound that is not dependent on. Thank you. Yeah.
Are there any further questions? I see some questions in the chat.
Right. So it depends on which. Right. So Victor. Okay. So there's a question. Let me go in order. Let me start by Raphael. If G is large and directed by finite of size n, let T be the first time at which all agree. Do you have example of G where you can say something about the size of T? Right. So that's a very good question. It's actually a very good open question. Maybe I'll mention in the context of this result. So in the context of this result. So here a very good open question is we don't know anything about the time. In the previous results. Time for agreement. So nothing is known about the time.
Could this be related to cover time questions?
I mean, by nothing we know about the time, we don't know that it's less than 2 to the 2 to the 2 to the 2 to the power of the number of nodes in the graph. When I say nothing, I mean nothing. Right? We really know nothing about the convergence time of these processes. So and somehow these are interesting questions that we thought about. We know nothing about. There's one example which is a Gaussian with improper prior, where you can relate it to properties of the graph. So this is in a paper. There's a bunch of paper. You can look in some of my paper with Omer Tammuz. There's also earlier work. So there is have some bounds in terms of the size of the graph. But in all the other graphs, we don't have any bounds. It's kind of, and the proofs are very soft, so they don't translate to anything quantitative. And this is, I think, is a very interesting problem to look at. Is it important that everybody takes action simultaneously? Yes. So right. So this is somebody asked about. In principle, it doesn't matter. In practice, I mentioned another weakness of this model in terms of the modeling. In order to carry out this, let me maybe read the question. Is it important in the model that everyone takes action simultaneously? We could also take actions according to independent Poisson process, for example. So it doesn't matter too much in the following way. I think many of the results still hold. But what's necessary for these models, and that's a problematic assumption that people in economics also complain a lot about, is that in order to carry out your Bayesian computation, you have to know the structure of the full network. Now, if you also take actions at a random time, I think at least the most obvious adaptation of the proofs would require that you know at which time people took their actions. Okay, so that's one of the reasons that people may be not looking so much about it. Right, so I think I talked about the fixation time. Nothing is really known about it, except for this, in this case of this very simple Gaussian model with improper prior. Yeah, I think it's possible to add some delay in the information. Like I said, most of the results are very soft, and I think most of them will carry over to the case where there's some delay when you get the information. These are all a very good question. Thank you, Michelle. Thank you, Victor.
There's a hand raised by Ganesh.
Yes, Ganesh, you have another question? Thanks.
No, sorry, I should lower my hand.
No worries.
So, anyone has another question? If not, I suggest that we all unmute ourselves to thank Elchanan for this lovely talk. And we should take a 5-minute break and start again at past 5.